Good afternoon, everyone. Today I wanted to speak about probing key physical parameters in hot stars using ESPaDOnS CFHT. So first, I want to recall what we know about magnetism in hot stars, and what we know is mainly thanks to CFHT and ESPaDOnS. Over the last 15 years, we have had a few large programs and PI programs that gave us a lot of answers about magnetism in hot stars. In particular, we now know that about 10% of hot stars are magnetic if they are single stars. But in close binaries, it is rarer to find magnetic hot stars. It's only about 2% of the hot stars that are magnetic in close binaries. The magnetic field at the surface of these stars at the pole can vary between 100 Gauss to 30 kilogauss, but typically you see the distribution on this plot here, bottom right. It peaks at 3 kilogauss. This is the typical field strength of a hot star. And the magnetic field that we observed in these stars are very simple structures.
Coralie, sorry, we don't see your slide changing.
Oh. So I was showing on the bottom right that the distribution of magnetic field strength peaks at 3 kilogauss, but can vary between 100 Gauss and 30 kilogauss. And the structure of this magnetic field is usually very simple. They are just dipole most of the time, but these dipoles are inclined compared to the rotation axis of the star. And these magnetic fields, they are stable over decades. Since we discovered them, they did not change. There are several stars that we've been following for decades. And they are very stable because they are of fossil origin. That means it is not the star that generates the magnetic field like in a dynamo in the sun or so. It is a magnetic field that was present when the star was formed and that got trapped in the star. And so it is stable with time, apart from the fact that because the magnetic axis is inclined compared to the rotation axis, we will see the magnetic field under various inclination as the star rotates. So that is what we know about magnetism in hot stars, but there are still a lot of things we do not know about magnetism in hot stars, and that is what we want to study now. And in particular, we want to understand the role of magnetism on various phenomena and physical ingredients in the star. So we want to know the role of magnetism on the internal structure of the star, for example, but also on the stellar environment, circumstellar environment, on the evolution of the star and the evolution of the magnetic field itself as the star evolves. We want to understand the interplay between magnetism and other physical mechanisms, for example, between magnetism and pulsations, between magnetism and binarity, how magnetism influences the chemical abundances. And to study these things and understand these physical properties, we have several ways to go. And I want to concentrate here on two. First, Magneto-asteroseismology, which is a seismology of magnetic pulsating stars. And this can help us understand what happens inside the star, so the internal structure, and in particular, the radial rotation profile. But also it gives us information about the magnetic field inside the star. All we can observe with ESPaDOnS is what happens at the surface, but we also want to know the magnetic field strength and topology inside the star. We can also look at binaries, and in particular eclipsing binaries, because then we can get exquisite parameters for masses and radii in particular, and we can understand the formation of magnetic fields. And for example, I told you that there are only 2% of magnetic hot stars in close binary. We are wondering why. One explanation is the fossil field scenario, because if the medium in which the star is formed is highly magnetic, it will inhibit core fragmentation. So it's harder to make a binary star when the medium is magnetic, but you can get a fossil field in a single star. But there could be other explanations. And for example, some of the magnetic stars may appear because of mergers. So two stars, hot stars that merge can create a magnetic field. And in this case, the merger is a single star. So there would be more magnetic single star formed through this channel. Also, we can think about the tidal effects in binary system that can disrupt the magnetic field. So the magnetic field could disappear in the binary star. So there are many scenarios, many explanations possible, and we want to try to understand which one is the good one. So to answer these questions, tackle these issues, we've created the MOBSTER collaboration about 3 years ago. MOBSTER stands for Magnetic OBA Stars with TESS, probing their evolutionary and rotational properties. And Alexandre David-Duras, Dominique Baumann, and myself are the co-PIs of this collaboration, which is composed of about 60 members from all over the world. And the goal of MOBSTER is to leverage the information from test data to learn more about magnetic stars. And in particular, test data help us to better select the magnetic candidates so that we can immediately concentrate on the stars that are likely to be magnetic. And then we can also combine the information we get from the high precision photometric data from tests with the information we get from ESPaDOnS data, spectropolarimetric data, and putting this information together, we can try to answer the questions I just mentioned. So why can we use test data to select magnetic candidates? Because magnetic stars show rotational modulation in their light curve. In the case of massive stars, O stars, and early B stars, this is because the wind particles are forced to follow the magnetic field lines around the star as they escape from the star. And the particles coming from the two magnetic poles will collide at the magnetic equator. This will form a magnetosphere. And this magnetosphere is in the magnetic equator, which means it is inclined compared to the rotation axis. And we will see it under various inclination as the star rotates. So it's like an eclipse of the star by the magnetosphere that changes with the rotation phase. For the cooler B stars and the A star, what we see are chemical spots at the surface. They come from the presence of the magnetic field inside the star. There are diffusion processes that create patches of overabundances or underabundances of chemical elements. In both cases, it results in a light curve like the one you see at the bottom here, which is a test light curve of a magnetic star. And you very clearly see this rotational modulation due either to a magnetosphere or to chemical spots. So if you see this kind of modulation in a test light curve, it is very likely that this star is magnetic. And this is how we select our magnetic candidates. So we tested this method on a pilot program. We concentrated on chemically peculiar stars. In 2020, Emmerich et al. Published a paper where they published a catalog of 1,000 new chemically peculiar stars that they discovered with LAMOST. We cross-correlated their list with the list of test targets. And from this sublist, we selected the brightest targets, and we looked at all the test light curves to select those that show rotational modulation. And we ended up with 48 targets that were observable from CFHT with ESPaDOnS. And 36 of these targets have been observed last year and this year. And for 36 observed magnetic candidates, we obtained 35 magnetic detection. And for one star, we had a very low signal to noise. In fact, the CFHT team did not validate this data, but we still looked at it, and the signal to noise was too low to detect anything, but that does not mean the star is not magnetic. So we have a 97% success rate in field detections in our target, but in fact, we could even say 100% because this one, very low signal to noise, should probably not count. And in the list of Emmerich et al., there was also some stars that were flagged as possible chemically peculiar star, but doubtful cases. And we observed one of them to see if they are really magnetic stars or not. And the answer is no. This star was not a magnetic star and not a chemically peculiar star. In fact, it is a binary. And probably most of these doubtful cases in Emmerich et al. Are binary stars. So I think we can conclude from this that our target selection is really working well. So the proxy we've used to select our target is excellent. And all the stars we observed, in fact, are magnetic. And you see one example of the magnetic detections here on the right. The bottom is the mean intensity profile of the lines in the spectrum. And the top here is the sub-V signature, so the presence of the magnetic field. So the detections are very clear. That's what I wanted to point out. Now, detecting a magnetic field is not enough. What we need to do is characterize the strength and the geometry of this magnetic field so that we know the properties of the magnetic field. And for this, we need the whole time series of spectropolarimetric observation between 15 and 20 observations per target. And of course, we cannot follow up all the stars that we have found to be magnetic. That would take too much time. So we concentrate on the most interesting targets, for example, those that are pulsator or eclipsing binaries. And in addition to using ESPaDOnS CFHT, we've tried to transfer the easiest targets to NeoNarval at TBL. Easy target means targets with a very strong magnetic field, typically 10 kilogauss, rotating slowly and very bright. And still, the signal to noise with NeoNarval is much less good than with ESPaDOnS. But for this easy target, it can be enough to characterize the stars. And so this follow-up has just started this semester, so I don't have any full-time series to show you yet, but I'm showing you another star we studied recently to show you what we want to do once we have a full-time series. We look at how the Stokes view profile changes with time, and from this, with Zeeman Doppler imaging, we can recreate the map of the surface of the star, so the magnetic field at the surface, but also, for example, the chemical maps. Since this pilot project has worked very well, we decided to extend it to several classes of targets to probe the various key physical parameters that we're interested in. And we grouped these targets in two categories, but this is a bit artificial because some stars could fall in various categories. So we want to look at pulsators with the aim to do Magneto-asteroseismology. So these are beta-Ceph stars, slowly pulsating B stars, delta Scuti star, gamma Dor stars, rapidly oscillating AP stars. We look at binaries, in particular eclipsing binaries that have a chemically peculiar component, but also heartbeat stars. These are very eccentric binary systems that have pulsation that are tidally excited. We looked at various stages of evolution, for example, pre-main sequence stars, big stars, but also more evolved stars like blue horizontal branch stars. And finally, we look at stars that show chemical peculiarity, but that do not have obviously a magnetic field, such as Mercury manganese stars and lambda blue stars. In these stars, we think that there may be ultra-weak fields. And all our targets that you see on the HR diagram on the right have been selected thanks to the test data. We took the stars that show rotational modulation to get very good candidates. So I cannot show you all the science we want to do with this data, but I have taken a few examples. First, Magneto-asteroseismology. The magnetic field has a very strong impact on the pulsations in the stars. And for example, when you observe pulsation frequencies, if there is a magnetic field, the pulsation frequency will be split into a multiplet. And what this multiplet looks like in the observation, for example, in test observation, depends on the magnetic field strength, but also on the inclination, the obliquity of the magnetic field compared to the rotation axis. And you see this on the figure on the left side. This is a 9 solar mass star with a relatively weak magnetic field, an inclination angle of 30 degrees. And the only difference between the top panel and the bottom panel is that we have changed the obliquity of the field compared to the rotation axis by 10 degrees. And because of these 10 degrees, you see that the amplitude of the peak in the multiplet of this pulsation mode are very different. And when you will observe this, this is a model, but when you will observe this, if the noise level is around here, you will see only 2 peaks in this case, but you will see 4 peaks in the bottom case. And so the amount of peaks you see, the multiplets you will see, depends on the strength and obliquity of the magnetic field. So it's very important that you know in advance what the magnetic field is in the star before you try to identify the pulsation modes that you can find with tests, for example.
You have 1 minute left, Coralie.
Okay, yes. The field also modifies the shape of the period spacing of the pulsations. So here you see in blue the curve of the period spacing without the magnetic field, and orange and green show what happens if there is a magnetic field. So in fact, looking at this pulsation tells us something about the strength and geometry of the internal magnetic field. So to summarize, we combine spectropolarimetry with seismology, so spectropolarimetric data with seismic data, and then we can do a magnetoasteroseismic model. And this model is much better constrained when there is a magnetic field, because, for example, if the magnetic field is higher, stronger than a certain critical value, we will know that the overshoot should be 0. There will be no overshoot when there is a strong field. Another example is eclipsing binaries. Today we know only 2 eclipsing binaries with a magnetic component. And these eclipsing binaries are very important because they give us very precise parameters, stellar parameters. And thanks to our selection with tests, we have many candidates now of magnetic eclipsing binaries, and we want to characterize them. And we hope it will help us understand why magnetic stars are so rare in closed binaries. And finally, my last example is the case of ultra-weak fields. For AM stars, Mercury manganese stars, and lambda Boöte stars, we see chemical peculiarities at the surface, but we do not see magnetic fields like we see in the other hot stars. And so there is a big question that how can we explain these chemical peculiarities? For the AM star, a few years ago, we picked the easiest targets, very bright, slowly rotating, and we obtained a lot of spectropolarimetric observation of 4 AM stars to get very, very, very precise spectropolarimetric observation below 1 Gauss precision. And we found that all of them are in fact magnetic with ultra-weak fields below 1 Gauss. And you see 2 examples of detections here. And we now think that maybe it's the same for Mercury manganese and lambda Boöte stars. Maybe they host ultra-weak fields. And that would mean that even an ultra-weak field has a very strong impact on hot stars. So to conclude and summarize, test data allow us to very efficiently select the magnetic candidates. With that, we can be much more efficient when we go to ESPaDOnS, to CFHT, to find these stars and characterize their magnetic fields. And then we can combine the information we get from the test data about pulsation, binarity, etc., with the magnetic properties we get from ESPaDOnS. And this allows us to really understand the physics that is at work in these hot stars. And the final goal is really to understand hot star formation and evolution. Thank you very much.
Thank you.